Hello, in this video I'm going to explain to you how a neural network works. And this is the first of a series of videos. In this part I'm going to try to get through some of what is involved in forward propagation. In the next video I'll finish that forward propagation and then also start talking about the back propagation. And then in the video after that, I'll talk about how we can use Python and Numpy to actually program a neural network ourselves by hand. And I think you'll find it surprisingly not that complicated. So let me go through it now, and hopefully you're able to follow. But please let me know if you have any questions related to anything I'm talking about in here. So in our as an example that we're going to use actually with our code in Python and just talking about it right now, we're going to use the MNIST dataset, which is a collection of grayscale images of hand-drawn digits from 0 through 9. So each image here is a 28 pixel in height by 28 pixel in width for a total of 784 pixels. You can find this data set right on Kaggle.com. I'll provide a link though in the description, so no worries there. So as you can see from the image, each row contains a label, and which is the number that these pixels represent. And there's 784 more columns after that first label column. And each pixel makes up one of these images. And each pixel can be a number between 0 and 255, which is common in grayscale images. And I'm only showing you kind of part of this, but there's actually, in the data set, there's about 40,000 rows, so plenty of data to use to train our neural network. And, of course, the goal is to train the neural network to be able to accurately predict the digits based on the pixel values, thus making our own little digit recognition AI application. So one thing we need to do before we get into the neural network components is we need to do what's called transpose the data set, which means each row is now becoming a column. So this is now a column. So we basically took this and flipped it 90 degrees, if you think about it that way. So the top of each row is now the label, not shown in this picture, but which image this column represents, right? And the remaining 784 rows in this column are the pixels. So this makes it easier for us to perform the calculations that we need to perform. Each column in our input data for the neural network now represents one of these images, right? So we'll examine each column one by one and perform calculations and produce the values that go into the hidden layer and the output, and then figure out what the prediction was, right? So we can have, speaking of which, you can have many hidden layers in a neural network, but we're just going to have one in our example. Also, the number of neurons, each of these circles represents a neurons. The number of neurons in the hidden layer is arbitrary. There are formulas you can use to determine the right amount of neurons and the right amount of layers in hidden layers that there should be. But for this example, we're just going to keep it simplified. And actually, in practice, a lot of times it is done arbitrarily as well. So just to recap, the input layer has 784 neurons, and that is dictated by the number of rows in each column in our database. So we don't choose how many neurons are in here. That's kind of dictated to us. However, the hidden layer is up to us, and we chose, for this example, just to have 4. Our output layer will be 10 neurons, and that, once again, is not up to us. That is determined by the amount of labels, right? The different possibilities. And there's 10 possibilities, 0 through 9, for our labels, right? and thus there's going to be 10 neurons in this output layer. So to find out the values for our hidden layer, we need to use the weights and biases, which I'm going to explain to you what they are in a second, and calculate the dot product. Dot product is if you've done some advanced math, you're probably familiar with the dot product function. So let's get into that then. I'm going to show you this image here, which I think is a nice demonstration of how dot product works. As you can see, each neuron in the input layer is assigned a weight, right? And they're assigned a weight for each neuron in the hidden layer. So this first neuron in the input layer has 4 weights because of 4 neurons in the hidden layer, right? And so the weights are initialized to a random number between -1 and 1. Each neuron in the hidden layer also has a bias, and it's typical that that is assigned to 1 at the start of the program. So random weights between -1 and 1 and a bias of 1. So to calculate the dot product, you multiply each neuron in the input layer, the value, by against the weight. So as you see here, this input is 250. It's multiplied against the weight, the first weight, and then the second neuron in the input layer is multiplied by its first weight, and then so on until you multiply them and then sum up everything, and then you add it to the bias right here, right? And that value, whatever that value is that you get, that is now the hidden layer neuron 1's value. And you would do the same thing now. You would go for to find out the value of hidden layer neuron 2. You do 250 times 89, 0 times 81, and 29 times 30.39. And so that, and again, you just follow this process, get the dot product, and those are your 4 values. So I'm going to stop there at the moment. There's a few more things that we'll need to do before we get to our output layer. But I think that's enough to digest. Please let me know if you have any questions, and look for the next video. Thanks.